In this video, we are going to look at a non-parametric test for multiple population proportions. In the previous video, we considered a dichotomous population in which an individual either had a trait or did not have that trait. Now we're going to let individuals fall into several categories. So I'll start with an example. Historically, the proportions of blood types A, B, AB, and O in the United States have been 0.41, 0.1, 0.04, and 0.45 respectively. A random sample of 200 Americans was selected and their blood types were A, 89, B, 18, AB, 12, and O, 81. Is there sufficient evidence at the 5% significance level to claim that the current proportions differ from the historic values? So I'll give you an example. AB had 12 out of 200, or 6%, but the historical proportion was 4%. Our question is that significantly different? So we want to note that this problem has a single categorical variable, and that categorical variable is blood type. So an individual can fall into one of four categories based on their blood type. Our null hypothesis is going to be that the historical proportions are still true today. In other words, the probability of being an A blood type is still 41%. B blood type is still going to be 10%. AB blood type is still going to be 4%. And O blood type is going to be 45%. Now, I would like my alternative hypothesis to be exhaustive so that it is including all the possibilities that contradict the null hypothesis. So instead of saying that all the proportions are different from the historical ones, I'm going to say at least one of the proportions is different from the historical values. So at the end of the day, with this test, I'll be able to say that at least one of the population's proportions is different from the historical values, but I won't be able to say which one. So our goal is to find a measure of the sample data that quantifies the strength of evidence against the null hypothesis. So we need to find a statistic and then be able to run a test to quantify that strength of evidence against the null hypothesis. And so that test is going to be the chi-square goodness of fit test, and it's proposed by the British statistician Karl Pearson in 1900. And what we're going to do is we're going to calculate the distance of each observed frequency from the expected frequency. So for example, the observed frequency of AB blood type is 12 out of the 200, but we expected that 4% would be AB, which is 8 out of the 200. So what we're going to do is we're going to sum over all the categories to find this chi-square statistic. So here, this is the Greek letter chi. And the thing that we're going to sum up is the difference between observed and expected frequency. We're going to square it, and then we're going to divide by the expected frequency. Okay, and here the expected frequency is going to be the sample size n times the proportion that we expected it to be, p sub I, where n is the sample size there. So if you look at this chi-squared statistic, what we're doing is we're looking at how far observed frequencies are from expected frequencies. We're going to square that, kind of like we squared these quantities in a variance calculation, right? That'll make the difference positive, but it'll also reward the differences being closer and then penalize the distances being farther apart. We're going to divide by the expected frequency, first of all, so that the units match, so that because we've now squared the numerator, so if we divide by expected frequency, we're going to get back to our original units. But the other reason is we want to make sure that this statistic doesn't really depend on the sample size. So we want to scale all the numbers by the expected frequency. So let's look at some observations about the chi-squared statistic. If chi-squared is small, the observed frequencies are going to be close to the expected frequencies, and that suggests that the data agree with the null hypothesis. So if OI is close to EI, we'll get a small chi-squared statistic that agrees with the null hypothesis. But if the chi-squareds are large, the OIs, the observed frequencies, are going to be far from the expected frequencies, and that suggests that the data disagree with the null hypothesis. And so the idea is that if we get a chi-square statistic that's large enough, then we'll have enough evidence to reject the null hypothesis. So it turns out that this statistic, the chi-square statistic, follows a chi-square distribution. That's pictured here. And I want to note some things about the chi-square distribution. First of all of the error is in the upper tail. So unlike the t-distribution or the normal distribution that trails off as you go to positive or negative infinity, here all of the error is going to be in the upper tail because it's only the upper tail that trails off as you let things go to infinity. And so a chi-square in the lower tail will correspond to observed frequencies being kind of close to expected frequencies. But otherwise, if the observed frequencies are much bigger than the expected frequencies, or if the observed frequencies are much smaller than the expected frequencies, we'll get a large chi-square statistic that'll put you in the upper tail, and that will allow us to reject the null hypothesis. So continuing on, the shape of the chi-square distribution is going to, again, depend on degrees of freedom, like the t-distribution. And the degrees of freedom is actually going to be k minus 1, where k is the number of categories. And so why is this the case? Well, the sum of the proportions in the category should be 1, right? If you sum up all of the A, B, and O blood types, that should give you all of the population. So it turns out that the last variable is defined by the others. So if we want to know how many free variables are, well, that in fact is going to be the number of categories minus 1. Something I wanted to mention about the chi-square distribution is that previously we learned the t-distribution is the distribution that's most natural to compare means. Well, the chi-square distribution is actually the distribution that you would use to compare variances. And that's essentially where this comes from. And you can see that there's elements of the chi-square distribution that kind of look like the variance calculation. Okay, so to conduct our chi-squared test, we're going to calculate the chi-squared statistic and the degrees of freedom. Then we're going to look up a p-value for the chi-squared distribution in a chart that I'll show you momentarily. And then if my chi-squared statistic is bigger than the cutoff of our alpha value, we'll be able to reject the null hypothesis. Otherwise, we cannot reject the null hypothesis. We could also say if p is less than alpha, then we reject, and then otherwise we cannot reject. So first we're going to calculate our chi-squared statistic. I want to remind us of the null hypothesis that the probability of an A blood type is 0.41, the probability of a B blood type is 0.1, the probability of an AB is 0.04, and the probability of an O blood type is 0.45. Okay, so we have 89 observed A's, okay, but 41% of the 200 were expected to be A's. That comes out to 82. What we're going to do is we're going to take 89 minus 82 and get 7. Okay, and then if we're going to do observed minus expected squared, that'll be 7 squared, and we're going to divide by expected, which is 82. That's going to come out to 0.5506. Okay, so for B, we have observed of 18. Expected was supposed to be 10% of the 200, which is going to be 20. And that's going to tell us that the observed of 18 minus expected is going to be -2. And so we're going to take observed minus expected squared, -2 squared. We're going to divide that by 20. So that's going to be 4 out of 20, right? Which comes out to 0.2. For our AB blood type, we have observed is 12. Our expected was 0.04, 4% of 200, which was supposed to be 8. Okay, so observed minus expected is 12 minus 8, which is 4. So that's going to give us 4 squared over 8. So that's 16 over 8, which is going to be 2. And then finally, for our observed, we had 81. So that's expected was supposed to be 45% of 200, which was going to be 90. And so we have 81 minus 90, which is -9. So we're going to have -9 squared over 90. And if we get -9 squared, which is 81 divided by 90, that's going to give us 0.9. And so now we can add all these up. So if we add all of these up, we're going to take the 0.9 plus the 2 plus the 0.2 plus the 0.5506 0.06. That'll give us our total chi-squared statistic, which in this case is 3.6506. Okay, now we need to check that against our chart. So I'm going to open up the, actually I'm going to just revise this really quickly. Made a mistake when I calculated this first one. So it turns out that 49 over 82 is in fact 0.5976. And so if we add up all of the chi-square statistics, or all of the, the observed minus the expected squareds over expected, we're going to get 3.696. Okay, so that's our chi-square. And so now we want to look at table 9 from our book. This is in the back of the textbook. Okay, so I'm going to go to the chi-square table. Our degrees of freedom for this problem is 3 because there are 4 categories. So k minus 1 is 3. And then our chi-square statistic is 3.696. You'll notice that ends up being to the left of the alpha equals 0.2. Okay, and so reading this table, we don't do anything about doubling any values or anything like that. We just look for where our statistic appears in the table. And in this case, it appears to the left of the 0.2. And so therefore, we can say that the p-value here is bigger than 0.2. And so therefore, we cannot reject the null hypothesis. And there is not sufficient evidence to suggest the blood type proportions or the are currently different from the historical ones. And so we can say at least one of the proportions must be different from the historical ones. And that concludes this chi-square goodness of fit test.